Hi everyone, this is Safa. In this video, we'll dive into the core of how autonomous underwater vehicles AUVs actually move. We'll explore the physics behind it and finish with a basic dynamic model in MATLAB that we'll build upon in the later video. AUVs are free to move in three-dimensional space. That means they experience 6 degrees of freedom, surge, sway, and heave, which are linear motion, and the roll, pitch, and the yaw, which are angular motion. Our model needs to account for all of them. To describe motion, we need to define frames of reference. The inertial frame is fixed to the earth or water. The body fixed frame is attached to the AUV and moves with it. Forces, velocities, and control input are usually written in the body frame, and positions are tracked in the inertial frame. We represent the position and orientation using the vector eta x, y, z for position and phi, theta, and psi for orientation. That's roll, pitch, and yaw. The velocity vector nu includes linear velocities u, v, w, and angular rates p, q, and r. Okay, the kinematic equation relates a velocity to change in position using a transformation matrix J eta. This is the full dynamic equation of motion for an AUV in 6 DOF. It accounts for the AUV's inertia, hydrodynamic effects, damping, gravity, and buoyancy, and the control inputs. This model is nonlinear and complex, but it's essential to understand what our controller will deal with. Let's now look at how the model looks in MATLAB. We'll write a simple structure that reflects the dynamics we just saw, not a full simulation yet, and just the layout we'll use. Okay. Here we define the state vectors, eta for position and nu for velocity. The matrix M, C, and D represent mass, correlates, effect, and damping, simplified for now. The gravity, buoyancy vector, J eta is 0 here, but we'll model it later. Okay. And finally, we compute nu dot the acceleration using the simplified dynamics equation. This gives us a clean base to build simulation and controllers in future videos. Okay, you can pause and copy the code. Run. Okay, as you can see. As expected, since we applied a thrust of 10 newtons only in the surge direction, we get an acceleration only in u. All other acceleration are zero for now, but later when we introduce a realistic mass and damping matrix, the response will be more interesting. Okay. To summarize, AUVs have 6 degrees of freedom. Their motion is described through kinematics and dynamics equation. We now have a basic structure in MATLAB that reflects these principles, and we'll build upon this in the next lesson. Thanks for watching. This is Safa. We're learning together one concept, one line of code at a time.